campus. You cannot hear me?
Get closer.
Oh boy, this is going to be difficult. This is how close I have to be?
Yes.
Good.
Turn it up, please.
I shouldn't have to be this close to the mic, I don't think.
Closer.
Closer?
Yeah, that's good.
That's where I have to be.
Pull the mic out.
Okay, why don't we try this? Does this work?
Yeah.
Oh, I've never actually held a mic and talked before. Now you're like causing me to pat my head and rub my tummy at the same time. This is going to be difficult.
Like a superstar.
A superstar, that's okay. Okay, so I'll be honest with you, this is I've been working in energy research for the last 15 years or so, working a lot in entrepreneurship, focused on really kind of the economic end of how to make this work. And I just put together this talk today, so you guys are you're getting my guinea pigs, yes, and I expect this to be a little bit controversial, and the question is whether I should hit the record button. Should I hit the record button?
Yeah.
Yeah, okay, so how do I do this? Record. Did you hit it yet? Oh, you've already recorded. You did it before I even got their approval. So I hope that you guys will interrupt me if you disagree or have some good comments. Not interrupt me so much I have to get through my talk, and I've got 40 slides, but hopefully you'll interrupt a little bit. Okay, so this is my lab. I owe it to a lot of my undergraduate and graduate students for the work, some of the work I'm going to present here, as well as Michael Lowick's lab in environmental studies, who's been a really important collaborator for us, as well as Brad and Lee Bebop's lab at NASA Ames. They live in Santa Cruz, so they've been really wonderful collaborators throughout this. So I want to start by talking about what I mean by balancing the food, water, energy nexus, what everybody else means, and kind of put the thing in context. So that the context, of course, there's trade-offs, right? You can't actually grow food without using enough water. You can't generate energy without using up food, for example. And so the question is what these trade-offs are, and what do you do to basically minimize these trade-offs or optimize so you don't actually have to have trade-offs at all. And that's what my talk is about. How can we do this so we don't have to have trade-offs at all? So a lot of you probably know about the food for fuel dilemma, right? When the ethanol crisis happened, you've all heard of that, right? So what you probably didn't hear about quite as much is the water for fuel dilemma. And that is there's a huge water footprint in biofuels. Okay? It is in fact much bigger than the water footprint in petroleum products. And so there's an inherent trade-off between how we handle our water resources and if we're going to go the biofuel route, how we generate fuels. Now you can argue whether we have to go the fuel route. I will argue in the end that we do need to have biofuels. There will be a debate about that, but partly because the energy density is much greater than batteries will ever make it, right? But so this is the dilemma. Of course, there was a whole bunch of very bad press on this whole thing about saying that we're using all our ethanol to grow corn, using all our corn to grow ethanol, and so people are going starving, right? So there's an inherent food and fuel trade-off. It's gotten, and there are other trade-offs. They're similar, not so much at food, but in ag. This is, of course, the burning of the crops in the rainforest down in Brazil to grow sugarcane for fuels, and of course, this is now what Borneo and Malaysia is looking like right now because of all the trade-off for growing oil palms to grow fuel. And so oil palms and sugarcane look really good for biofuels. And so there's a huge destruction of rainforests in order to generate those fuels. There's also a trade-off for wood and food for electricity. You always hear about the huge amount of water that agriculture uses, but in fact thermoelectric power generation, not hydroelectric by the way, but thermoelectric uses actually quite a bit of our water resources, our freshwater resources. Hydroelectric doesn't, of course, but one thing you have to worry about hydroelectric is it's currently 17% of power generation in the world and 70% of our renewable energy generation. Yes?
What's thermoelectric mean?
Thermoelectric is basically any time where you heat something and turn it into steam to turn a generator. So that's nuclear, coal, oil, pretty much our entire energy infrastructure. Yeah. So So it ends up that that's 70% of our renewable resources right now. It's one of the most rapidly growing renewable energy resources. Also, it's going to tap out soon. But climate change is a real problem to hydroelectric resources, right? Because you're changing the distribution of water, which means you're going to change the efficiency of the power plants. A big rap, solar power, sun power got a big rap recently because they bought a PV. You know, one of the problems with PVs in the desert, you have to clean them frequently, so they use a lot of water to clean PV panels. That's a problem that I don't think people have ever completely addressed. And then I want to show this thing down here. This is a solar array in the middle of ag lands. Just a few years ago, the Farm Bureau sued Fresno County for permitting PV farms on farmland because it took it out of the Williamson Act, which is a tax credit given for people to have tillable land. And they were turning to PV panels, which is completely, against the tax policy. So it ends up that 1/3 of the PV panels right now are going up in arable land. Okay? In places where people, in California. So you have to remember there's a trade-off now between PV panels and PV installations and growth of crops, okay? So that's what I mean by trade-off of food and electricity. And we all know, I don't have to go spend a lot of time in this, we all know, of course, that water goes into food. That's that other 37% of that pie chart. You can, what you might not know is about is a lot of energy goes into food also. It's not nearly as much as other energy, but it's still a measurable thing. And I just showed this graph here so you get an idea of how much. Something like half of it goes to refrigeration and packaging. Okay, so there's a huge energy footprint to food. And you can, I pull this graph, I'm going to show it up to you again, but these, the 2025, this map up here are the areas that we're going to have basically real issues with water usage very soon, and you can see that India looks really bad. So India is the hot spot for everybody right now. Africa to a lesser extent. Africa is going to be growing importance for a reason I'll bring up a little bit later. So we already have this energy, food, water trade-off right now. But the point is it's actually going to get worse for two reasons. One is population growth, and I'll go in those numbers a little bit more in a little bit. And the other is climate change. And there's been a lot of people that have processed the numbers for, what this is going to mean. And what they know, if they look at the numbers, is that just by 2030, let alone further on, we're going to need about something like 50% more food and energy than we currently produce. Remember that all takes up water. And we're also going to need, on top of that, 30% more fresh water. So we've got, there's some big competing demands now at this food, energy, water nexus we've got to figure out how to deal with on a fairly short time scale. And then climate change, of course, isn't sitting in the background affecting all of these things. Okay. So here's the typical population growth diagram, and I divided up by nation because, the dashed lines are projections, and the things in shades are, we don't know exactly what the population is going to grow, but we have a pretty good idea, right? The point of this is to show where the problems are, or why people are focusing on certain areas of the world. You can see Asia is going up quite a bit between 2010 and 2050, but Africa's going through the roof. Okay, so now that means that the problem is going to switch very shortly from India, which will be the near-term problem, to Africa, is what everybody's predicting will be the big challenge later on. No one's particularly concerned about Europe and North America, right? Okay, I'll just tell you that right now. We live there. And of course, Latin American is another area that's a growing concern. So if you look at this, and where there's growing concern, if you look at Asia and Africa and you look at this map, it kind of looks like everything's coming into in terms of the impacts of climate change and water resources and everything, it's those two areas that will be the hot spot. You will notice that there's this problem in the middle of the United States called the Midwest, and that will be a big problem also. It's because the predictions of water is worse in the Midwest than it is, for example, in California in terms of precipitation changes. So that's what happens to population growth. That's the pressures population is going to have on us. And then there's the pressures that climate change is going to have on us. So we've got the global warming predictions. You know, they're all over the map, they're predictions, right? But pretty much we know we're going to get hotter, and we know certain areas are going to get hotter faster than others, in particular places like India, Africa, parts of South America. It ends up the United States isn't going to change that much. It'll get a little warmer, but it's not as dramatic as a lot of the other problems going on. And then there's going to be a large change in precipitation, right? You know, water is a conserved quantity, so we're not going to lose water. We're just going to move it to the oceans, which is a problem because we don't collect it from there. So what happens is we're going to just move water basically to the poles and lose it in the middle of the country and in places like, you know, Australia and India and parts of Africa and the Midwest. We're going to lose it in the Midwest. So those are the... I mean, what happens to California is kind of up in the air right now, but those are the stringent. I want to bring up, and of course what companies add is seawater rise. We know we're going to have at least a meter of seawater rise. We can't do anything about that. This is a map of the San Francisco area, and you can see that 1 meter puts San Francisco Airport underwater. That's okay. They know that's going to happen. There's ways of dealing with that. You know, the Dutch have figured that out. It's just expensive. Down below, I show you what the 100-meter sea level rise. You know, you can say, oh, that's never going to happen soon. Okay, but you can see we lose Louisiana and we lose Florida. Okay, and we lose your vacation spots down the Yucatan Peninsula, right? And this might seem like it possibly can't happen, but we can learn a lot from our past. And I'm going to look at, put up this graph because I think it's kind of telling. Now, this is the climate change through history. We've had huge climate change in history, much bigger than what we're anticipating going through in the next few hundred years. And so you have a lot of these, there's uncertainties or estimates, but we know some of the numbers pretty well. And this is basically the atmospheric CO2 and the average global temperature based on, you know, how many millions of years ago. And I want you to look at this specific area known as the Carboniferous period, which basically generated all the fossil fuels we use today, which were responsible for our standard of living right now. Okay, so this is an important time period in our past. And what you can see, if you look quickly, is the CO2 levels were pretty high, like 1,500 parts per million when we started that period. And the temperatures are really high, say like about 20 degrees Celsius. And then you'll see halfway through that period, there was a huge drop. In fact, an event that led to mass extinctions. And we ended up generally cold and with low CO2. So the numbers look like something like this. So this is what it looked like when we started. And I'm going to show you this just because it's going to be important later on. It was a swampy mess, right? Continents were all thing. We were a swampy mess. We had really, really big insects, right? Pay attention to the insects. They're going to come back. And O2 levels were 35%. Oh, we all breathe really well, even on Mount Everest. And it started very warm and wet. But then there was something known as the Carboniferous rainforest collapse. The sea levels fell. The sea levels fell 100 meters. Okay, roughly, give or take, you know, I don't know exactly, but something like that number. So we have had periods in the past where sea levels have changed dramatically. Now, of course, this is the opposite direction. They're falling because what's happening is the CO2 levels are crashing. They're going down. We ended up this period at about 350 parts per million CO2, or where we are today. And we ended up colder, 12 degrees Celsius, but not all different to what we are today. Okay, so this is that led to the rise of the reptiles, which of course was led to the Jurassic period, and then we are sitting, of course, in this really weird location on the CO2 map, right, with relatively low CO2 and relatively low temperatures. So we kind of know what's going to happen because it's happened before. Okay. So the question is, how does climate change affect that balance I mentioned earlier between water, energy, and food? And you think you kind of understand it, but then you start looking at the details and it starts becoming somewhat more complicated than you think. So, for example, this was an article that just came out this year, Sierra Nevada Snow and California's Thirst, by one of the professors down at UC Merced. And he says something very interesting. He says, basically says that trees also affect the amount of water stored in the mountains simply by growing, because they suck up water from the ground. Warmer temperatures also mean that trees grow faster. So CO2 causes plants to go faster. We know that. That's why we generated all the carbon, all the fuels we have during this area where CO2 is very high, right? And don't necessarily shut down the winter when you've got warmer winters. That means, basically that means is that the plants grow more, they suck up more water. So the process of plants growing sucks up more water, it also sucks up more CO2. So you've got a transition between, you've got a trade-off, inherent trade-off in climate change between the sucking up of CO2 and the use of water resources. Okay, you've got to pay attention to this because it's going to be important in how we figure out how to move forward. And then on the opposite thing, we have this. I don't think this movie's going to play, but I will try. Whoops. What happened?
The leading southern flank of the Butte Fire blowing up as down canyon winds start to move. A sea of sparks and flame
Picture of a
here.
fire
We're
that
just
means
a
a
little
lot to
east
me.
of San Andreas, where this fire is continuing its march further into the foothills. The Butte Fire has now metastasized across 65,000 acres, nearly 100 square miles. And then eating the flames again burning uphill, cutting off this road. One reason firefighters have to be so careful. These erratic winds have shifted 3 or 4 times in the last hour. Another reason the Butte Fire is still so dangerous.
So this was a fire that hit exactly about a year ago, give or take another week from now. I was there shortly after this, so I saw a lot of the damage shortly after. It destroyed structures. This is actually our house. Right there. It was hot enough to actually melt the wood burning stove. But then the question is, this is going on all around California. In this particular case, it was $2 billion of damage. That's $2 billion pumped into the system, by the way, to rebuild it in a potentially sustainable manner. 1,300 homes and 2,000 structures. We're trying to rebuild. We're trying to it's 20 acres. We're trying to build this into like, a net zero, DOE net zero home with a place for students and other people to do research on terms of how to recover after fires in a sustainable manner. But it's very hard to do that. And the reason why it's very hard to do that is after this fire, and this is happening all over California, there were over 1,000 cannabis, this is 900, this is outdated, 1,000 cannabis permits applied for this county, which only has 35,000 people in the entire county. So that would be equivalent to 900 cannabis permits in the size of Capitola. Okay, just to give you an idea, the county gets $5,000 for each of those permits. Okay, they get $4,000 to process my housing permit. They weren't willing to process my housing permits. They sent it out to Sacramento to process. Okay?
Oh my God.
So these are going to become cannabis hotspots. That's how we're going to rebuild after the fire. You can argue whether or not that's the best way to deal with the balance between CO2, food, and water when these are both ag lands and vine lands and various other things. And this takes a lot of water. On the other hand, well, I'm not going to discuss that. I'll discuss this later. Anyway, so it's an interesting thing about how to manage lands in California after the fire. I thought this was really good. The guy got the Butte Fire tattooed on his arm, right behind his pot plants. Okay, so the question, and I just basically painted you a whole bunch of doom and gloom, and is there a solution? And I wouldn't be here if I didn't think there was. I do think that we can keep the earth looking like that, and hopefully keep it green and beautiful, like that picture presents. But we do that, we have to really understand our water and energy budget of the earth and how to optimize that water and energy budget in a sustainable manner so you're not inherently exchanging one for the other. So this is our water budget, and we all know it's, we've all learned this in second grade, right? You've got transpiration, condensation, precipitation, right? Exactly. Evaporation, condensation, precipitation. You all heard that song, right? My daughter knows it. And the thing I want to focus on is what the plants do. So the plants do a couple things. There's about 10% water runoff. That's somewhat of a concern, particularly in California when you have fertilizers in it, but you can deal, but that's a generally positive, collectible thing. You also have 50% water that infiltrates in the soil. That's probably potentially okay, although it depends on how it infiltrates and how much you contaminate it because it goes back into the ground table. It's the 40% water that evaporates and transpires that we don't lose. The Earth keeps it, but we lose it from our local area. It moves someplace else, and frequently it moves someplace else and drops water where we don't need it. Right. So that's the movement. So it's the evaporation and transpiration area that I want to take a closer look at. There are experts in the audience, by the way, over here on the groundwater who probably have a lot of great things to say about groundwater. Bruce Daniels is right over here. So there is a potentially, however, fairly very easy solution to the transpiration evaporation route, and that's basically covered agriculture, what we also know as greenhouses. This gives you an idea of the amount of water used in open agriculture. It depends on the crops, but it's between something like, I don't know if this is per hectare or whatever, but it's basically, this is a comparison chart, 60 to 600 liters. If you put it in a greenhouse, it depends on the quality of the greenhouse, etc., but the numbers drop dramatically. In fact, it's not unusual to have an order of magnitude drop in water use per crop produced going to covered agriculture. Okay? Not only that, but the numbers are that increase the yield per unit hectare by 4 times to 10 times what you can do in open field. Largely because you can do vertical very easily inside covered systems. It's harder to do that because you don't have the frame support in open fields, right? So this is a typical tomato growing plant inside a greenhouse, for example. There's an advanced greenhouse going in Saudi Arabia, for example, that reduces the water needed in that particular cinch from 250 liters per kilogram to 3 liters per kilogram, so almost a factor of 100 decrease. And the reason why is because you don't have to worry about the water going to soil because it actually just goes back in the water because they're mostly hydroponic systems. You don't worry about evaporation and transpiration because that's all collects water. It all condenses on the roof of the greenhouse. The greenhouse then all funnels the water back into the system, right? So we know how to grow food in large quantities with very small water resources. We already know how to do that. There are some clever solutions, clever approaches to also try to make this a little bit better. I put this up because it's something I've been looking into quite recently. And this is a seawater greenhouse. In this case, they're trying to say, well, can you just operate the greenhouse completely off salt water? And then the math works out. You just basically pipe the salt water into a porous cardboard that absorbs the sun. That's enough heat that it provides the steam. The steam comes off as fresh water, which you pump over. You have cold seawater coming in that condenses the steam into water. That collects in the freshwater storage. And then you basically take the slightly saltier seawater and you pump it back to the ocean. Seems like, oh, you're putting saltier seawater back in the ocean, but you're already putting fresh water into the ocean. It's not a huge impact. Yeah?
What do you do with the salty cardboard?
The salty cardboard is a problem. That's a very good question. So you either have to recycle it, which may be difficult, or come up with a better approach. So there's a good engineering challenge on the salty cardboard for you. But I think it's solvable. So that's the one. Those are starting to go up now in areas which have no water, but have close access to oceans. So I hope that, well, maybe I didn't convince you, but I think you can deal with the food-water trade-off. There are technologies already available that you can grow plenty of food and plenty of water with less water resources currently. So the question is, how do we deal with the energy? And by the way, none of this has to do with anything I'm doing right now. Okay, we're gonna get to that. So this has to do with part of it has to do with how to make that economically feasible, right? We don't do it now because it's not economically feasible. So I'm going to address how we actually make it so it makes sense. So this is the Earth's energy budget. We all know what this is a very complicated graph by NASA, but basically you have sun, you have the solar energy, it gets absorbed by the surface, it ends up about 0.6% of the sun makes it down to the surface from the atmosphere. The surface gets emitted, and then there's this back radiation, which has to do with the carbon dioxide and other greenhouse gases in the atmosphere, and that's the number that everybody worries about, that back radiation number. You can point out that we're talking about very small changes in that back radiation number having huge changes in our overall temperature, okay? We're not talking about, these are not major changes. So I'm really focused kind of on down that side, and really I'm looking at what to do with the sun that kind of hits the Earth. So this is the sun that actually comes down outside the atmosphere, down to sea level that we see. This is the spectrum versus the function of wavelength. You don't like looking at things at wavelength, don't worry about it. It's a black body radiation curve, but the important thing is where visible light sits in our purposes, which is in this 400 to 700 nanometer range of the spectrum. And we can look at that a little bit closer. And, you know, blue's down at 400 nanometers. That's the UV. That's the stuff that's really bad for you because it's high enough energy to break bonds, carbon bonds in your body. 700 nanometers is lower energy. It's use it for all sorts of things, mostly for heat. So that's the range. And if you look, and there's a weird quirk of fate that chlorophyll, which is the main material in plants, doesn't absorb most of the visible spectrum. It absorbs none of the UV and none of the IR. And absorbs actually even a very small, tiny fraction of the visible spectrum. That's why they're green. They're green because they reflect green light, and green light is where the sun spectrum comes close to peaking. Okay, so there's a whole bunch of reasons why that may happen. A lot of people think it's because purple bacteria evolved first, and that the chlorophyll came up on had to access the light, and the only way to do that over purple bacteria was to be absorb only the blue and the red. Okay, but there's a whole debates about why plants are green. Anyway, so the point is that the plants use less than 20% of the sun's energy, which basically gives you the ability to, if you can just use the other 80%, you can actually do energy production and food production on the same piece of land. So that's one of the technologies I'm working on. I have, one of the companies, it's my research, one of the companies is called Soil Culture. We basically make panels that only take the energy of light that plants don't use. So this is how it works. It's very simple. We use this very luminescent red glowing material. It absorbs the green portion of the spectrum, which plants don't use at all. It converts it to red very efficiently at about 85-90% yield. That light waveguides down, just like your optical fiber communications waveguides down. It gets converted to power by PV panels. We use standard silicon PV to do that in little strips. Some of the light isn't waveguided. Waveguides do not have 100% efficiency, so some of the light comes through, but the light that comes through is red light, which the plants really like a lot. So the fact that we've blocked a little bit of light with the silicon PV cell is completely made up by the fact that we've enhanced the light in the red portion of the spectrum, which plants love, okay? So it uses standard crystalline silicon PV assembly, which means it's really cheap. Here's one installation we have. I can't remember, this is in Southern California. There's always questions about lifetime. I can tell you that they live long enough. They have over 20-year lifetime, these luminescent materials in air, because we found the right material. Okay, so there's something called aquaponics, aquaponics, which is fish and plant combination. The problem there is that it's extremely difficult to get the nutrients from the high enough concentration in the fish to basically fertilize the plants effectively, and you need really high fish densities, which can be somewhat not healthy for the fish. I think aquaponics could be good. I'm actually more interested in bioponics or organic hydroponics. So basically ways in which of doing hydroponics but with using natural materials as opposed to artificial materials. Aquaponics is a type of bioponics that's using fish as the ingredients. I do have an aquaponics system running in our greenhouse if people want to look at it. Yeah.
Is the red panels, are they like a dispersed material? Is that an optical coating?
It's in a plastic sheet. If you've ever seen a glowing like clipboard or a kid's toy, you ever had those kids' toys that glow kind of pink or fluorescent yellow or fluorescent green? You guys have no idea what I'm talking about, right?
No, I know.
You know what I'm talking about, right? It's very similar material.
Is it like a conversion or just absorption or something?
It absorbs the, it's a photoluminescent material, fluorescent material. So it absorbs the photons and re-emits photons.
So it's a different wavelength.
Exactly. So it absorbs photons in the green and it re-emits photons in the red by fluorescence. And it does it very efficiently. I'm not going to go through all our plant trials. Needless to say, we have done a lot. Okay, so we have tested these at the UCSC Arboretum. If you come there, I'll tell you I have an open house on December 1st. You can see my greenhouses, including our aquaponics setup. We did a clear greenhouse and the red covered greenhouse just to prove whether or not it hurt the plants. We know that the data looked either neutral or positive. We did a big, but those greenhouses were small. We did a big installation in Southern California. We did a big installation in Watsonville. We did installation in Canada, up in Alberta, about 6 hours from the Arctic Circle by car. So we know it works in cold climates. We worked with City Blooms. We've done an installation with City Blooms, which is a hydroponic startup in Santa Cruz. It works there. This is a big installation we just did down at KB Farms, about a 30 kilowatt installation. So we know that that it doesn't have a negative impact on the plants. In some cases, has a positive impact on the plants, but in many cases, it's at worst neutral. And that's okay because we're getting the power out at the same time that we're growing the plants. That's what we need to prove. Yeah. Was there a question back there?
Oh, I was just saying to the cannabis growers using that stuff?
Oh, yeah. Now you brought the can of worms up, right? The question is whether cannabis users want to use this thing, right? You know, the NSF won't fund us if we, like,
I'll answer.
generate, build greenhouses for cannabis users. Does that answer your question? Yeah.
How do you keep the greenhouses from getting too hot? Because that's really the main deal.
Right. Well, this works really, really well because we're taking out all the high energy light that would normally go in and heat the greenhouse if the plants don't efficiently use. That would hit and reflect off the leaves and heat the leaves off. We're converting that directly to power, so our greenhouses are actually cooler. It'd be kind of like equivalent to putting those shades up, but you don't have to put shades up because we're taking that energy out. Yeah. We take out about of the photoactive spectrum, it's about 20%, but of the whole solar spectrum, it's closer to 30%, something like that. Yeah.
Can you repeat the questions?
Yeah, the question is what the efficiency of the PV panels is. It depends dramatically on how many of the PV cells we stick in versus the luminescent material. We balance that based on our cooling needs of the greenhouse and the needs of the plant. So it's anywhere from, say, 6% power efficiency, area efficiency, because we have 100% coverage, to 10%, depending on how much PV panels are. It literally depends on how much light the plants need. We can always increase, our panels, we can get the efficiency up to 20%, but it'd be solid black, right? And plants would die. So there's an interesting balance between how you balance that. I'm sorry, PV is photovoltaic. Photovoltaics, which is the same thing as a solar cell. So it's something that takes particles of light from the sun, which are photons, and converts it directly to electrons, which we use for electricity. Yeah?
How do you handle pollination in such a closed system?
How do I handle what?
Pollination.
Oh, that's a really good question.
That's the question.
No, it says not all plants need pollination. Tomatoes do, right? They need bee pollination. They can, bees are used quite a bit in greenhouses all the time, so pollination is really easy. I think it's kind of somewhat of a questionable practice, the way they do it, because the bees kind of like die off in a month and they buy new bees. But the red light also affects the color tuning of the light also affects the pollination, because some insects, bees trigger off UV. So we have to make sure we have UV. So there's a lot of interest in adding back UV light. All greenhouses have that issue. So we're looking at UV. I'm not talking about UV lighting. I also do solid state lighting. We're looking at UV LED lighting in greenhouses to get rid of powdery mildew and to deal with the pollination issue. But all greenhouses have that problem, because if you have glass, you cut out the UV light. Yes?
Don't you have to use water to keep greenhouses clean?
You do have to use water to keep greenhouses clean, but they already use the water to keep the greenhouses clean. So we kind of feel like, and you can recover it to some extent off the greenhouse roof because of the gutter system. So because they already have to clean the roofs of the greenhouses anyways, they're cleaning our panels at the same time. It's kind of a net neutral. We're not adding to the water footprint. But yes, you do have to clean them. You will see sometimes people put greenhouses, they'll put this white wash over them. They'll just junk white paint all over the whole thing, and that's to keep the heat down. We don't have to do that because we already have the absorbers in there. But then they have to wash off that white paint in the wintertime. Yes?
In terms of scaling this up as, like as a real solution on a global scale, I'm wondering what the energy footprint of building all these greenhouses would be.
That's a good question. I will tell you that, the main energy, the question is what's the energy footprint of building the greenhouses? The main energy footprint, as I understand it, is the glass, but you have to use glass for the PV panels anyway. Every single PV panel has a glass. So there's an energy footprint when you make photovoltaics. So I don't think we're adding to the energy footprint that much by building the greenhouses. The metal frame will also have some energy footprint, and that's a big question about how big that energy footprint is. But we're not adding to the glass footprint, assuming that you want to put PV up anyway. And the PV energy payback now is down to 1 or 2 years, depending on it. Yeah. Yes.
So what's the cost of manufacturing these panels, the red panels? How do
Boy, you guys are just like
We're doing this soon.
okay, right now we're pretty expensive because we're doing it in our little teeny 1,000 square foot warehouse in Scotts Valley. So we're closer to $2 a watt, but we think we can get down to $1 a watt with just even remotely scaling the manufacturing. Does that answer your question? Yeah. But the problem, these are all engineering challenges to get the cost down. We can do it. Anyway, there's no reason why it should be more expensive than conventional PV though. I can answer that. So the question is, what about fuels? So we actually looked at fuels also. You know that most of our fuels came from the algae and other rampant plants grown during the Carboniferous period. Algae is getting a lot of bad rap these days, but it's responsible for a lot of the fuels we use today. But algae actually has very, very rapid growth rates, something like 10x normal plants, which basically means that's also why it's a pest, right? Because it has very rapid growth rates, which basically means that it consumes CO2 at very high rates, and which is one of the reasons why it was so prevalent when CO2 is higher. And that basically means that if you want to basically produce enough fuel, and you do it with algae, you can do it with a lot smaller footprint. Okay. Now, the problem is, of course, algae requires lots of water. We can solve that in a closed atmosphere. It's easy to contaminate, but we can also solve that with a closed atmosphere. I don't have a solution yet for the higher expense, but that's something that a lot of other people are working on. They do grow in salt water also. There were some things going up in the ocean, but there's a problem with getting the salt water. So the question is, does it work? Getting the stuff from the ocean to the shore. So does it work? The ends up algae, you can pick any color you want. It's really nice. We picked green because our panels work with green. Lee Bebot did a thesis. Her thesis, which is unpublished, basically showed that algae grows really, really well under red light, which made her a really good collaborator to work on this. So we did a lot of trials on algae using both mini troughs and test tubes in our greenhouses with various different forms of algae. This is the one on the left is the control growth, and the other ones are just different colors of light of the luminescent material. Dark means a very high concentration, so we're shading a lot, and light means a very low concentration of luminescent dye, which means we're shading very little. And what you should generally see is that the luminescent dye doesn't hurt the algae growth, in some cases maybe even helps it, so that these panels, so it looks like algae and biofuels would grow really well under these greenhouse systems. This is a marketing slide. I really hate to put this up, but everybody asks me, well, why don't you just put what's the point of putting the greenhouses on the panels on the roof? You can just put the panels right next to the greenhouses. And panels are really cheap, so that's a very attractive option. The problem, of course, is that uses up the land, so you can't grow crops on it. If land's valuable, that's an issue. because the panels, the solid panels kill the plants, right? The other big issue for us is that we save a lot of money on the racking because we don't have a separate racking for the panels. We use the same racking for the greenhouses and the panels, so it saves a lot of money on the racking cost. Moreover, right now, it happens to be there's a 30% federal tax credit for installing PV in your houses. You guys should all take advantage of that while it's still going. It's just been approved, so install it. But that means we can write off 30% of the greenhouse structure. Okay, so that makes the greenhouses a lot cheaper. Now, granted, we're taking advantage of a tax incentive, but that means we can put greenhouses up a lot cheaper than we were before because they're holding PV panels. I want to mention that there's other cool technologies that people are starting to work on, and I'm even starting to look on, and that is the wonderful thing that now that it's getting hotter and our temperatures are rising, things that weren't practical before are now starting to be practical. One of them is solar cooling. Solar cooling uses solar absorption chiller heaters. They need pretty hot water to work efficiently, but now that it's getting really hot in India, it's looking like it might work in India, which is great because air conditioning is probably the biggest challenge we're going to have, the biggest near-term challenge we're going to have with climate change. Greenhouses if you do it with greenhouses, you have the advantage that you can spike the temperature anywhere from 15 to 20 or 30 degrees Celsius. We've even gotten as far as 40 degrees Celsius higher. That makes the entire efficiency of the solar cooling more efficient. You can also, of course, use greenhouses for heating. They're already used quite extensively for heating in cold climates. Now, this is an example of a solar chiller system in Saudi Arabia. They converted this entire warehouse over to solar chillers to cool. Okay, so think that there's no reason why energy and food have to be in opposition to each other. You can basically, because plants don't use that much of the sun's energy, there's no reason why you can't generate power on exactly the same footprint you're generating the food. Okay? Yes?
What about meat?
Meat! I will get to that in a second. Okay. I don't know if I'm going to answer for you there, but I'll talk about it. And because you can balance food and water and food and energy, you get energy and water out kind of just as the balancing the equation sort of thing. So I haven't talked yet about this impact on climate change. So the big impact, what's my time? Do I have time to talk? I have about 5 minutes left, 10 minutes left. I think I have enough time. Okay, so you guys are so generous. Carbon farming. You guys have heard of carbon farming, right? There's a big project up in Marin to farm for carbon. Oh, well, okay. Well, this basically means, so we know that the carbon in our soils is less than it was basically 100 years ago. We're sucking out the carbon of our soil. So the obvious place, the obvious challenge is, well, if we can just figure out how to put the CO2 back in the soil, the carbon back in the soil, that kind of solves our problem, right? That's known as carbon farming. It's a big movement right now. In fact, we'll have someone talk about it if you come to our thing in February. I'll get to that in a second. So the idea is we understand, how our gases and CO2 consume. We can basically take the plants and actually fix the CO2 into carbon down into soil carbon in the soil, and that's a way to basically remove CO2 from the atmosphere. A lot of the stuff like biochar, etc., people are proposing, or cement are really proposed to do just that. So why is carbon farming attractive? Well, carbon farming is attractive because of plots like this. These are areas that we know that there's a soil carbon gap, that we have not enough carbon in the soil compared to what we think we should have had based on just historical data. So you can see there's lots of parts in Asia, there's some parts in the US, parts in the rainforest that we think that we can use as big carbon sinks. Okay. So there's that going on. Now it ends up greenhouses are great. The problem is we have trouble using the carbon sinks. We have no way of pulling the CO2 out and getting it in. Although we could just build tall trees and do it that way, but that takes time. So right now it ends up that we take CO2 right now and we dump it into greenhouses because plants don't really want to grow at 350 parts per million. They really want to grow closer to 800 to 1,000 parts per million. Okay, so some plants prefer 1,500 parts per million. So greenhouses purposely throw CO2 into the greenhouses to grow better. So the greenhouses, as long as it's covered, we can contain the CO2. It becomes a place where we can actually use them now to fix stuff in the soil. Here's an example of data of different rice species, etc., that grew under different parts per million. What you can see is at 800 parts per million, the rice grew more than at 300 parts per million, or at ambient, which is 390. This over here is a dry ice experiment. This is a cannabis grower. Cannabis comes up a lot here. Sorry about that. This is a cannabis grower who just took dry ice and hung it up in milk cartons and uses the evaporation of dry ice because the density goes down, the gas goes down, and uses that as a CO2 source. Dry ice is CO2, for those people who didn't know, and uses that to add to the growth of his plants. So, but the point is you have to have a way of containing the gas in order to convert it. Or you have to grow really tall trees and plants and keep the rainforests, which is another solution. Now the problem is, the reason why you can't just do it in an open field is the other problem with increasing CO2. Remember I showed you those huge, gigantic insects at the very in the Carboniferous period? Insects, love it. High CO2 levels and high plant levels. They start taking over the plants. There's a lot of publications out right now that say that increasing CO2 isn't helpful, even though it looks like it should be helpful because plants grow better under increased CO2 because you have insects take off, right? So that's why you need a closed structure. It's the only way to keep the insects out and the insects. Okay. Okay, so this is another one. This is another undiscussed thing that's really important that's coming up. It's going to hit very soon. It's already hit, but I'll bring it a little bit more. And that is, it ends up that CO2 might not be the worst greenhouse gas in the near future. Okay. Yeah, exactly. So it ends up that methane's a really bad greenhouse gas. 1 pound of methane is equivalent to about 21 pounds of CO2 in terms of how it warms how it sticks in our atmosphere and it reflects the radiation down. It has to do with the bottom, it's a chemistry problem, but trust me on this. And you can look at, everybody sees the CO2 parts per million, sees this really beautiful rise, but no one really looks at the methane CO2. And if you look at the methane, it's going up faster than CO2. And we haven't concerned ourselves before because if you look at the CO2, it's in parts per million. You look at the CH4, it's in parts per billion. But you can see that they're already off by roughly an order of magnitude, and I'm multiplying by 20, so there's another order of magnitude. So what it basically means, you can kind of do the math and stuff, is methane's going to catch up with CO2. Not soon, but at some point, but it might. I can't say for sure it will, but it might. It's a concern. And that's the reason why cows and meat is considered really bad CO2, really bad for the environment and really bad for climate change is because they output a lot of methane. Okay, we output methane too, but they also do. So there's been some questions about what to do about this if you're not going to just stop eating meat. And some fappy farmer, you guys have all seen this picture, right, with a little gas tank on top of the back of the cow, with the little thing. You guys are eating, so I probably won't go into it. But that's one solution. It's probably not a very practical solution, right? Okay, but people are looking, and I would say decomposing crops also put out methanes, right? They produce gas. That's the basis of anaerobic digestion, which we use for producing biogas, which is very important. So people are starting to look at ways of covering fields and collecting the methane. So you can imagine if you could, grow meat or crops under a controlled environment where you could collect the methane. That methane can not only be collected so it doesn't become a greenhouse gas, but it can also be used for a fuel that could be very useful for powering things like cogen plants. Yeah?
Even if you were able to control the methane with cows here, remove cows or whatever you choose to do, there's another huge methane source in Africa. Huge termite mounds, as high as 12 feet, and there are so many of them. There are tremendous numbers of them.
Wow, that's interesting. I didn't know about that. I don't have a solution for that. I'll have to think about that really hard. Yes.
I thought another source of methane was the melting of the permafrost, where it's faster than it seems to be.
Yes, that's a problem too. Yep.
What did I say we
Yeah,
can't
it
hear?
definitely is. Another problem with the release of methane and stuff is the melting of the permafrost. It's getting sufficiently warm now that the permafrost is starting to melt, right? Well, CO2 and, yeah, various gases that will definitely cause climate. Okay, so the other thing I kind of breezed over right now is if you're going to fixate carbon, the question is, we don't really know exactly what plants we want to grow to do that. We don't even know really, it's even hard to get data on, you know, if we're going to replant after a fire, what do we replant to minimize our water and increase our CO2 consumption? There's some evidence, we know fires, you know, produce a whole bunch, there's some evidence that the fires in 1 year can produce as much CO2 emissions, can produce like 30% of our CO2 emissions in a bad year. But we also know that when the plants recover from the fire, they consume a lot. But we don't understand, we don't have good data on that. And the problem with that is the CO2, the measurement systems used for CO2 release and uptake measurements, which are photosynthetic measurements, are very expensive. They're about $15,000 to $40,000, and they require somebody, usually a student, like a graduate student, to go out in the field and take this little clamp and stick it on the leaf, and measure how this concentration depends on time, because you just measure the CO2 concentration. At time you can figure out how much the leaf is picking up CO2 or releasing it. I think that's, if we're going to try to understand plants across the world in different systems, how they uptake CO2 and release CO2, and particularly how they uptake and release water, because remember, water transpiration is very important. We need a cheaper system. So one of the things I've been working on is very low cost carbon uptake release and moisture uptake and release a sensing system. Actually, Lydia over here is working on that right there.
All right.
We're hoping to make it very cheap, and we'll put it, it's supposed to be open source, open line. We would tell people where to get their parts, and everything would be free to the community if we could get it to work, but we will see. Anyway. So the question is, does the math make sense? You guys are saying, okay, so you're telling me all this stuff. You're full of... Anyways, I'm not going to tell you how much it costs. That requires a little bit more time. But I'm going to tell you what the numbers are. So the potential cropland is about 8.5 billion acres. That's 34 trillion meters squared if you want to do the math, because we don't work in hectares like all the same countries in the world. We work in acres. It's 34 trillion meters squared. So I'm going to use 15 watts. The sun puts out about 1,000 watts per meter squared. Most panels will collect 100 to 200 watts per meter squared, but they don't do it all the time, so I'm going to derate that to 15 watts per meter squared. Okay. Multiply that out. That means we have 500 terawatts of power potential on our ag lands. And that's combining it with being able to grow crops at the same time. That's why I derated it. So, and the nice thing about ag lands is they're near population centers. You don't have to worry about infrastructure or anything like that. You're not porting things. And they also don't have to worry about environmental damage because they're already basically being used for ag. So if you cover about 10% of the land, you get about 50 terawatts. That's enough. That's enough to meet our growth and electricity needs. You can, talk about electricity, heating, and cooling, and blah, 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 but, it's the numbers are there. Because the covered ag, the crop yields are so much higher, you get the 40% food production, and then the water decrease isn't that much. It's maybe about 10%. You're only covering a little over 10% of the land, but you can figure out there's other solutions to the water also. To give you an idea, this isn't, this is Almeria, Spain. It's the greenhouses in Almeria, Spain. They grow 80% of the fruits and vegetables for Europe. It's so big you can see it from space. It's one of the few places that actually is undergoing global cooling right now because of the reflection from the panel. So it's not like we don't have these big solutions. Here's one from big one that's going in Europe and in Great Britain right now. You can see the size of a football field of that greenhouse. So people are starting to look at these larger scale systems. That's Almeria, Spain. It's on the southern tip of Spain. It's 100,000 hectares of covered. It's now mostly cheap greenhouses. It might not work without panels, but some of them would, yeah.
If you have that greenhouse, couldn't you just put the panels up on a rack over the field?
You could. The issue there is, do you get the containment for some of the benefits you wouldn't get. You wouldn't be able to take the water.
You wouldn't get the benefits, but you would have less cost.
Yes, you would.
And you may not get the insect.
You wouldn't get the insect. Yeah, you might not get the insect. It's good or bad, right? So there's lots of questions about which is the best way. I don't know the answer to that. So this is kind of the summary. I have a couple more slides of the summary. That is, I'm basically arguing, you can believe it or not, and that's okay, that we can solve our problems with greenhouses that have integrated advanced energy water sources. It doesn't have to be greenhouses, it could be covered ag. But the numbers, I was going to ask you, and you also need to basically be very careful on your land management. You can't just go ahead and decide you're going to put pot farms wherever you want to. You've got to think very carefully on how your water and CO2 consumption and energy deals with how you manage your land. Does anybody know what this is? Quiz.
Is it real?
It is real. It's in Arizona, I can tell you that. It's Biosphere 2. This man won the thing. You know when we built Biosphere 2? Wow. Why did we build Biosphere 2? Maybe you don't know. It was a self-contained ecosystem. It was an example of whether or not humans could live on Mars or some other similar place. They put people in here, they closed it up, and they said, can you produce enough food, CO2, water, with a zero net, no energy, in a closed ecosystem, nothing put in, nothing put out, for humans to survive.
Wait, did they put Pauly Shore in there?
Did they put who?
Pauly Shore?
I don't know. Did they? Anyway, it's an interesting challenge because the truth of the matter is we need to deal with these greenhouses whether we're not. Eventually the human eyes are going to deal with greenhouses. And the reason for it is very simple. We want to figure out how we're going to survive past whatever thing happens to the Earth. And this is why NASA's involved. You guys hear about the habitable zone quite a bit right now, don't you? You hear about what habitable planets are? You guys read about the new habitable planet that just got discovered, right? Yeah, okay. So this is known as the Goldilocks zone, or the habitable zone of planets. And the interesting thing is, this is the habitable zone in our solar system. You probably want to know what that was, right? Earth's in the middle. That's shocking to you. Mars is kind of on the very close to the edge. That's important. Yeah, exactly. Venus is over the other edge. Venus, maybe many years ago. I mean, Venus is a runner. You know, Venus is higher than Mercury. You guys know that? Venus is hotter than Mercury. Hotter. Does that make sense to you?
Yes.
Okay. It's a greenhouse. It's an example of a classic greenhouse gas run amok. Anyways, our sun's getting bigger. So you'll hear all about, we're warming because the sun's getting bigger. It's getting bigger, but it's not going to get bigger in your lifetime. You're okay. But what happens when the sun gets bigger is we become out of the habitable zone, and Mars gets into the habitable zone. Our oceans are going to boil, and we're going to lose our complete ecosystem. It'll be gone. So we're all going to be gone. The whole system will be gone about, I think they extended to 1 billion years from now. It was like 600 million, so I think we're okay. But there's other little things in the system that could really completely mess up our planet. You saw those numbers before when the climate change went from where temperatures got very high and numbers went to 1,500 and there are mass extinctions. Those things can happen too if an asteroid hits the area. So people are looking at how to colonize Mars. Mars looks like a really good candidate. We spend all our time looking at planets that we can never get to as habitable planets, and Mars is really not that far off. Okay. So greenhouses will play a critical role. You've seen the Martian movie. You should see it if you haven't seen it. It's a really cool movie. So understanding how we use these closed ecosystems to provide for us in the future are going to be really important. Anyways, that's it. I just have 2 plugs. I'm done. The S-Lab, my sustainability lab. It's a maker's lab space for students, innovators, and collaborators like you who want to work with students. I have an open house, December 1st. I don't know when. I know it's somewhere in my labs at the Arboretum and at TMN, but I don't know exactly where. But it's going to be open house for the community. If you guys want to come in and see what we're doing, you'll be able to do that. If you are interested in getting an invitation, email me at sacarter@ucsc.edu, and I'll put you on my mailing list for when the S-Lab opens. December 1st is our target date. And we also have we have greenhouses at the Arboretum for those people who are filming with the Arboretum. And also the Climate Science and Policy Conference is coming up. I think it's in February 2017. It's a great event. Yours truly is monitoring engineering panel. I guess a lot of great speakers that are experts, much more experts than I am, in terms of future technologies. Please make it to the event. And I don't have an email. Well, you can email me for that too, but I don't know what the email is for that. Yeah.
I wanted to ask you about, you said at the very beginning something about batteries. And Mr. Musk, Mr. Tesla, thinks he's going to save the world. And would you say why you think there might be other points of view?
Well, batteries are great technology, and I think that in some cases they need to be really used. Are they? But the point is that the energy density of a battery is still like an order of magnitude less than a fossil fuel. I don't think anybody's looking at making, airplanes powered on electric batteries or, rocket ships powered on batteries, right? You just don't have the fuel density. So, also the numbers on environmental damage and, energy consumption and water consumption and effects on climate change on batteries, and Tesla in particular is still out. Do I think that electric vehicles, that he's made a huge impact on electric vehicles going mainstream? Yes, I do. Am I a little bit concerned about, 1 billion cars being powered electric vehicles? Maybe, maybe not. It depends on what battery technology they use. But batteries are, there isn't a huge leap in gains to be made of batteries. So I don't think they're ever going to catch up in terms of, it'll be very hard for them to catch up in terms of energy per unit density versus a biofuel. Even a biofuel as simple as a piece of wood. Yeah.
You don't have to generate electricity by biology.
You are entirely correct.
Powered by solar photovoltaic. And there is, you don't have to take up land to do it. Say power plant.
Yes, you can. You're entirely right. There's a lot of really good technologies in ammonia. Yeah, so the question is, you do not have to generate liquid fuels with biology. You can do liquid fuels with chemistry, and he's entirely right. There's some very good process using chemistry to generate liquid fuels, which would have energy densities very similar to the liquid fuels the fossil fuels we've come to know and love. So yes, you are entirely correct about that. I'm not as familiar with those. I mean, I know people are looking at ammonia-based fuels, but yeah, the chemistry for liquid fuels is, I think, a big emerging area that might be much more important than people are paying attention to right now. So I totally agree with you. Yes.
Glad you mentioned solar absorption chilling. I've always been intrigued about that. Seems kind of like the killer application, because right when you most need it, when the sun's really bright and hot, is when you most have it, because the sun is providing the energy for this solar fueled cooling. But are there any places you know of yet where that's being, commercially applied, or?
Well, this picture I showed earlier in Dubai, it's being commercially applied. One of the leaders at UC in the UC system on solar cooling is Roland Winstead, who's at UC Merced. So he knows a lot about that. I just started in the last, I would say, 2 months, kind of looking at it as, are there science challenges there that are needed, or is it pure, is there anything I can contribute to that field? It's an interesting challenge to me. Anyways, yes?
This is a little bit of a shift in focus, but when you talk about the 10% of land with covered agriculture,